Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to the next lecture in this particular course on analytical spectral microscopy applications of inorganic compounds and nanomaterials. So far we have gone through quite a few lectures, particularly based on the analytical mode. We looked at atomic absorption spectroscopy. We looked at a lot of thermal methods, variety of thermal methods. We have looked at electrochemical methods. And today we will look at something on the magnetism, and which means magnetic properties. So these are also absolutely important in terms of the inorganic chemistry, coordination compounds, nanomaterials, and all alike in this. Okay, so when it comes to the magnetic materials, what comes into our mind is the paramagnet and the diamagnet. So you know very well the diamagnet is the one where the material is repelled by the magnetic field, and the paramagnet is the one where the substance is attracted by the field. The same example is shown here. Please have a look at this particular slide, and here it is a liquid nitrogen is poured on that, and the liquid nitrogen, as you know, that all the electrons are paired and it is completely diamagnetic. And if you look at the other one, which is where the liquid oxygen is poured here, the liquid oxygen, you know that dioxygen is paramagnetic, O2. So, and you can see that getting stuck between the two poles. So that's what is called attracted by the magnetic field. And here repelled means you will not see that obviously here, because they are all repelled away that. So these are the two basic things what we know, but there are many other things which are beyond. Using these concepts, the materials have modified a variety of the properties to become something like a ferromagnetic, and a few other things we will study just in a few minutes. So what are the ferromagnetic ones? Like the metals like iron, cobalt, nickel, gadolinium, all these kinds of things. You can also have ferrite with the other metal ion, like iron oxide with other metal ion. For example, here is a barium ferrite with other. So variety of these things. These things are all super the paramagnetic, which is ferromagnetic kind of a materials. So these ferromagnetic materials are used a lot in the read-write devices. We know read-write devices such as the old days it was floppies, now CDs, now even the hard disks. So you have all those kinds of. So you need to have the data recorded on that and then being translated. So one is recording part, other is translating part or reading part. You call translation is called reading. Now please draw your attention onto this slide. So you can see that it is the magnetic disc that you have, and a tip which is the reader tip. The reader tip will have a coil of this kind, and this plate will have this ferromagnetic coating. Below that you can have any non-conducting kind of things. So for example, plastic plate with a ferromagnetic tape, a ferromagnetic layer, a ferromagnetic material. So any of these things are one and the same, and now this goes through this particular recording head. This will either you can have this moving or you can have the tape moving. Either of that is there. That is not important for us. That is important for the engineers, which one is better, etc. For us, as far as the material property is concerned, this part is good enough. And now as it goes, when it reads, it creates a magnetic component. Therefore is induced, that means you have a south and north pole, that means there is an induction. So this is an induction of that, so that results in an induced magnetism. So that is how the magnetic property is the one which helps in reading, as well as same thing into the writing parts as well. So the recording and the reading parts of this. So these are mainly ferromagnetic material. Now there are other materials which are called, see, you know very well the normal conducting materials, but there are superconducting materials The superconducting materials means the conductivity is more or less instantaneous and without having much of a resistance at all, almost no resistance kind of thing. That is what the superconducting magnets. So these superconducting magnets, if you place, you can see that placing into these ones here, and you can have a train running on the rails but does not touch the rail. This will be a little above the rail, and that is what is called levitation. So this is a magnetic levitation. So what is the use of that? So you should not be frightened that this will fall down. No, it will not fall down as long as your magnetic field is holding that. So the magnetic field or magnetic force holds that one. There is nothing to worry about. As a result of that, you can get very high speeds, speeds such as 600, 500, 600. So why? Because the friction between the rail and the wheel is being removed now. So because this does not sit onto that. So more details of that comes in physics and engineering part of it, but just for that, for me, this is what I would like to. So what we have, in effect, I could show you some materials without magnetism, with magnetism, with a ultramagnetism, with a much higher conductivity level of magnetic things. So that means we know that there is a huge variety of magnetic materials possible. Then we will try to understand each of these a little better, and then look at some application, then look at some problems where we can put our effort to understand. First of all, how will a magnetic field comes in a molecule or in an atom? In an atom, you have electrons. Each electron will be spinning. So each spinning electron will have a component of the magnetic moment. So each spinning electron will have. Now we know that the many cases the electrons are paired. So you have a magnetic moment in one direction, magnetic moment in the other direction, and both are equal and both are opposite. In that case, it will become cancel each other. So this is also another. So that means most of the organic substances, if you look at, what do you have? The electrons are paired. If the electrons are paired, you will not have the net magnetic moment. So that is why you see most of the organic substances, organic compounds, or the diamagnetic kind of things. Of course, other than radicals, etc. If you have a radical, then that radical unpaired, cancelled electron will be there. In case of transition metal complexes, as you can see that a large number of transition metal ions have got their d electrons, some configuration or the other, in some state of the other, in some oxidation state of the other, there may be the unpaired electrons, and those unpaired electrons will be net not cancelled, so by the other ones. So therefore you can have a magnetism. So most often the magnetic properties come from the inorganic ions, complexes, compounds, composites, complex, all these kinds of things can give the variety of the magnetic property, and their magnetic properties can be modified by using a field also, temperature also. So all of these kinds of things, or sometimes different kinds of magnetic behaviors can be combined together and generate a new type of a magnetic behavior. These are the kinds of things we will see just at a little base level. Okay, paramagnetic, you have all these are not just the simple spins, they are the magnetic vectors in a true sense. So the magnetic vectors are which are in a loose term is spoken as the spins. They are randomly oriented, but overall there is a net the magnetization, because the spins or the vectors in one direction are more than the sum of all the other direction ones. So that is the paramagnetic. This paramagnetism can have a tampering, can have a adjustment, can have a rearrangement provided temperatures. So at some temperatures something can happen, at certain other temperatures something else can happen. This is what we will see now. So now you go to this system which is the ferrimagnetism. Now what you have a kind of an alignment, but it is not a complete cancellation. You see the red and the blue, please see at the slide. So the red and blue, the red and blue. So the size of the blue is shown as smaller, the size of the red is shown as a longer or greater, and that means net effect is not cancelled. So, that is what is called the ferrimagnetism. So, ferrimagnetic is a little bit greater than the paramagnetic in terms of the magnetic moment. Now, we go to the other. Suppose if this blue vector is as much as the same as the red vector, and see that is shown as red, red with the red, red with the red. So, one is the up, one is with the down. So, but they are equal. If they are equal, they are opposite, and then they will cancel. But this could happen in the compounds as a function of temperature, at which, for example, this is the Tn, that is Niels temperature. Below the Niels temperature, so these spins are completely anti-parallelly aligned. That means anti-parallelly aligned, not parallelly, anti-parallelly aligned. So, that means one of the vector, these are all vectorial values. So, therefore, one of the vector value is exactly compensated with the one which is in the opposite direction. So, if you call one of them as a positive, other as a negative, so you can see that the positive and negative getting cancelled out. If it completely cancels, that is what is called the anti-ferromagnetic. So, that means your paramagnetic behavior could get adjusted, okay, realigned, the spins getting realigned depending upon the temperature. That is what we are studying now. So, look at the one on the top, which is a ferromagnetic. So, here what you see, all of them are aligned in same direction. So, that means you have a plus plus plus, so you add all of them sigma. So, this can happen in some materials at some below certain temperature is called the Tc, the Curie temperature. The spins are all aligned parallel and therefore add up. So, here spins are all anti-parallel, they get cancelled. The spins are anti-parallel, spins are there, but cancellation is not 100%. Therefore, you have some ferromagnetic behavior. So, this is where that we need to look at. So, as I mentioned that paramagnetic you can see in terms of the pictorial, let us say in a compound in a normal state. So, you have the spins in different directions. Kindly look at the slide please. So, so you here you can see all these the spins are in random orientations, in different orientations. Now, if you put a field on that, so that same compound, you are not doing anything change, but you are putting under the magnetic poles. So, that means you are putting under a magnetic field, then you can see that they are aligned. Now, you remove the magnetic field, now they go back to the randomization of that. Such a material is called the paramagnetic material. Now, if somebody wants the kind of a understanding, the physics way of explaining is this one. Now, what is a ferromagnetic? The ferromagnetic is, so this is a normal material, could be a paramagnetic material, but at the room in the free conditions without any kind of a field, the spins or the magnetic vectors are randomly oriented with some positive gain. That is why you have the paramagnetic. Now, you apply a magnetic field, they are all aligned. Now, you remove the magnetic field, see that in the last one, please keep seeing the this slide, it is very important. So, when you look at this particular thing, so you have removed, but what is happening was it is not completely gone back like here. So, here all the spins have gone back to the random. So, it is not gone. There are certain regions and zones where there is an alignment better than other, etc. So, therefore, a better magnetization is being held in the compound upon magnetization of this. So, what a magnetization etc. will be seen after a couple of slides or so. So, we will look into that, do not worry. So, now you can see distinctly different the paramagnetic. So, where when you remove the field, the spins go back, and in the ferromagnetic they do not completely go back to the random, but there will be regions of magnetic vectors orientations are there. I hope that is clear. So, I have given you in the previous slide as a general example. Now, I have given you more of a physics oriented, where the spin need not be electron spin, it can be even the magnetic vector. Many times it is written as spin. Okay. So, that is where the thing is. Now, let us look at these things in terms of measurable parameter. What will you measure? So you said earlier there are spins going across, some semi cancelling, complete cancelling, and then adding. So all these things. So those should result in some parameter called the magnetic susceptibility. To what extent the material is susceptible for the magnetization. So magnetic susceptibility should be understood, to what extent the compound or the material is susceptible for magnetization. That is how one should basically read, to what extent. So in paramagnetic, in ferromagnetic, and magnets. So that means we will look at the behavior of the magnetic susceptibility. So what is magnetic susceptibility? So magnetic susceptibility is a chi, which is nothing but the magnetization that takes place when the field is applied. What we have seen earlier, a compound without any field, a compound with the field, a compound after removing the field. That is what we have seen. So that means under the field what happens? So under the field there are some changes that are happening in the orientation of the vectors, and that is what is leading to the magnetic susceptibility. The more the vectors, greater the susceptibility, lesser the vectors, lesser the susceptibility, means lesser the cancellation. So lesser the cancellation, obviously less susceptibility, and completely paired 0. Okay. So now that magnetic susceptibility is a ratio of the magnetization over the field. That means it is not always fixed. If I change the field, I can change, I can get the m also different, but the chi will be the same. Okay. So the chi is a ratio of my magnetic field, magnetization generated in the compound over that of the magnetic field applied, or magnetic field strength applied. Okay. And this is dependent upon the permeability, how well your magnetic rays can pass through. Magnetism we cannot explain by visual way. So when you put between the two magnets, without to our eyes there are many rays are passing through, and you are putting a sample in between. So therefore that is where things, suppose you have a magnetic pole here, so let us say n south, north south kind of a thing, then you have a compound here, so there are some rays going into that. So that is, you cannot see with the eyes. So these are the magnetic forces going through that. So how well they are permitted to go through is what is called the permeability. So for each compound it will not be it will be different. Not all compounds will have the same permeability. So different compounds will have different kinds of permeability. So this is another parameter. You can see that the permeability, the molar level, the mu O 1 plus chi kind of thing. Now let us look at this magnetic susceptibility behavior. Please have your focus on this slide here, and this is temperature on the increasing side, this is the chi on the increasing side. For a simple paramagnetic material, you are not applying any magnetic field here, you are only applying the temperature variation. So you are going from, let us say, room temperature to higher, or a very low temperature to higher, these kind of things. Higher means sometimes it could be room temperature, it will be higher, the low temperature will be the lower temperature. Now the temperature variation on this, so you have a susceptibility drops down as the temperature keeps increasing to quite a kind of an exponential kind of a decay. So this chi here is C by T. What is C? We will see here. Now if you plot this 1 by chi, so instead of chi 1 by chi and temperature, what you will get? You will get a straight line, and when you extend, please see on the screen this extend, then it will go through the origin, and the slope of this is the C. Okay. So the slope by temperature is your susceptibility, the slope by the temperature. Now what is for the ferromagnetic and what is for the antiferromagnetic? Now same kind of a plot, the chi m on the y axis, the temperature on the x axis. Now what happens is, generally what you do is, you always come from the higher temperature, means room, and then go down. That is how the magnetic susceptibility is measured. Now so we are starting here, even here also you start here and then go up. So you start here and then you keep going. Please look at the slide, please. So you can see this up to here, there is no substantial change, no considerable change, no great variation in the susceptibility. But at this point there is a sudden hike, and then gets saturated, it gets saturated. And this temperature at which there is a strong deviation from the usual value of chi, means in increasing side, and that temperature is called the Curie temperature. So again, that chi is C by T minus Tc. This is the temperature. So whatever the temperature that Tc, so the chi is dependent on that particular. Now for the antiferromagnetic, for example, for this ferromagnetic, you can see there 1 by chi curve. So the 1 by chi curve is here is a straight line, here also straight line, but in the case of paramagnetic it goes through the origin, but in case of ferromagnetic it does not go through the origin, but it intersects with the x-axis. X-axis is your temperature axis, and in a positive way. And for the antiferromagnetic, so you start from here, you increase the temperature, actually you are at the room temperature, you are decrease the temperature. So at one particular stage, so up to here if you see, how does it look like? Just like a paramagnetic. So from here up to here it looks like a paramagnetic. You see here, this behavior here and this behavior. Please focus on the slide please. Okay. Now at this particular temperature there is a straight fall in the value. What value? Y value. Y is what? Chi. So the chi value decreases there. So but is a sharp decrease. So here a chi value sharp increase is a ferromagnetic, a chi value is a sharp decrease is the antiferromagnetic, and that is what is the Néel temperature, and this is what is the Curie temperature. Now if you take the 1 by chi curve as a temperature, again straight line, but it cuts the x-axis in the negative side of that. Okay, so that is where the Tn comes into picture in that. So I hope the third way of explaining these magnetic parameters is clear with the quantification, where you can use a plot, and one of them is the temperature is a variation. Here you have not used anything with the field at all. Okay, so temperature variation on this particular thing. Of course you can apply the field and also do it, that's a different experiments, that for some other reason which I will explain you later. So these are the behaviors you can get for paramagnetic as a simple quenching kind of a values or increasing values of this, and a sudden increase for ferromagnetic and sudden decrease below a temperature for the antiferromagnet. So these are the kinds of things that are very important. I hope that it's not confusing. Hope you are able to follow that all these aspects of it. These are all very important. Now if you look at these values of the chi, they are all in the 10th power kind of things. So it's not very convenient to you always compare the susceptibility of one with the susceptibility of another. These are all 10 power minus something, 10 power minus some other value, etc. So these are not easy to compare. So therefore one can convert into the magnetic moment. Magnetic moment you are not measuring, you are just only converting by using a formula. What you measure is a magnetic susceptibility always, and you measure the total. So we will come to that. So if you look at that, the magnetic moment is nothing but your magnetic susceptibility multiplied by whatever the temperature where you are talking about, and the number of unpaired electrons present in that system under the square root multiplied by 2.84. We do not need to know the derivation of this. These are very well available in the literature. Wherever if you just click you will get it, but there is no need for this particular course. That is why I have not put. Okay, so the chi-m is a total molar magnetic susceptibility, as I have mentioned already. Mu effective, it should have been mu effective magnetic moment in Bohr magnetons. This value is in Bohr magnetons. N is number of paramagnetic centers, which means number of unpaired electrons in that. Okay, so now let us look at for the transition elements. Transition elements, so if you look at the electron, you will have the L value, you will have the S value. So the orbital angular momentum, spin angular momentum. For multi-electron, the total L value, suppose if there is more than one electron, like D2 system, D3 system, D4 system, etc., then you need to calculate the total L, the capital L with respect to all this. Please keep looking at the slide. Okay, the L1, L plus L2 plus L3, this whole thing will give you the total L value. And similarly, S value is of course is a half if they are all oriented in one direction. If they are oriented in opposite direction, it will be minus half. So that will be the summation of the all the spins. And so that is what, as far as an electron is concerned, that you need to look at the total, because you are putting the total compound in the magnetic field to measure. You are not putting some electron into that. Okay. So the total magnetic moment mu, with taking the component of L, taking the component of S together, that is what you measure. You cannot measure L separately, you cannot measure S separately. Okay. So you can calculate S, I will show you just in a while, then you can get the L value, you can calculate the L value also and show whether the same thing is present in the system or whether there is any quenching has taken place, all of those. So for an L plus S, this is the 4S into S plus 1 plus L into L plus 1 under square root in the Bohr magnetons. Okay. Again, this is all very well derived. I am not giving the derivation in this particular course, in this particular lectures at all. So kindly have you look at this slide. The mu S, suppose if I think that the L is 0, okay, in all this. So this component will go to 0 and this will become mu S. The mu S is square root of 4S into S plus 1 to the power half, that is square root, that is B Bohr magneton, and this can be converted all the spins which are aligned in the same direction, therefore n into small s or n into half. So therefore this is n by 2 into n by 2 plus 1. So therefore what is the thing? So n into square root of n into, therefore mu spin only comes from number of square root of n into n plus Bohr magneton, okay, n plus 2 into Bohr magneton. Okay. So that is where, so now if I put n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, etc., etc., then you put n is equal to 1 into 3 square root of 3. So 1.8385, 2 means 2 plus 2, 4 into 2, 8, 8 is less than 9, so therefore it is 2.83 in that range. So 3 plus 2, 5, 5 into 3, 15, 15 by square root, if it is 16 it will be 4, it will be less than 4, so 3.85 or something. So like that you will have. Okay. So you can see that the one electron 1.73, so please see the slide, 1.73, 2.83, 3.88, 4.9, etc., etc., for electrons 1, 2, 3, 4, 5, unpaired electrons. These are not magnetic spin as such, they are electrons in the compound, where it is not compensated out by, they are not paired up by other electrons. So this is found in the transition metals, or when you have some polarized system or a radical kind of a system in the organic kind of things. So I just showed one example here in the bottom just to calculate the S value. So the D system has got 5 the orbitals, right? So dxy, dyz, dzx, these things. So therefore you can use plus, otherwise you have to use the modulus value. So instead of using the modulus value, let us use in this way. So like this, if you have 3, if you have 4, if you have 5, if you have 6, if you have 7, if you have 8, if you have 9, if you have 10. So if it is 10, all will add, all will subtract, so it becomes 0. So if you have only 1, that will be 2. So capital L is, if you have L is equal to D2, well, if it's D1, D2, then you will have 1 plus 1, 2 plus 1, 3, L is equal to 3. So like that what you have. So if you have 3, so 2 plus 1 plus 0, that will be again 3, and then if you have 4, 2 plus 1 plus 0 minus 1, so this will cancel, will become 2, and 2 plus 1 plus 0 plus minus 1 minus 2, 0. So L value can go with these kind of things. I hope you get the idea of as how to do that. Similarly, S you can make number of unpaired electrons multiplied by half, that will give you that. So these are, so that means you can have a spin only which you can calculate, but whatever you measure is the total magnetic moment, always you measure. On the other hand, if you look for the lanthanide ions, so therefore the mu effective is mu SO, SO is spin only into 1 minus alpha into lambda by delta. So alpha is a constant which is depending upon the ground term of that. 2 for E ground term, 4 for A, that you do not need to go because these are all spectroscopy terms that we do not. The capital delta is the crystal field splitting, okay, and this lambda is the spin orbit coupling. That is, so to what extent the spin and the orbits are coupled. So, the greater the coupling, of course, the greater the value of that will be. So, for lanthanides, the spin orbit couplings are generally much greater than the delta value. So, delta value turns out to be small, lambda value turns out to be higher, whereas transition metals, delta value turns out to be greater, lambda value turns out to be smaller. Therefore, you can ignore many times, not always, many times the L component or L contribution. But in lanthanides, you cannot completely ignore the contribution of L, because that the coupling is much greater than these crystal field splitting. In F, crystal field splitting is smaller as compared to that. So, in that case, this is the formula which for mu, and the G parameters are defined here. G is with the S, L and J. J is nothing but the L plus S component. Essentially, for those below half filled, the J will be L minus S. Those which are above half filled, that means above 7, F7, that will be L plus S, and for 7 it is the J is equal to S itself, okay. So, you have below F7, above F7, F7. So, the J value that you can see, and the G value you can calculate from this. So, therefore, obviously the lanthanides are not showing the kind of a magnetization or magnetic moment which is just equivalent to spin, but many of the transition metals would show that, but with a little variation. Variations are small, but whereas the variations are large. These have a meaning in making the magnetic materials. So, there is a meaning for the transition metals showing lower the spin orbit coupling, the lower orbital contribution, and whereas the spin orbit coupling is greater, showing a greater contribution by the lanthanides. Both have a meaning, and now one can try to use these between lanthanide with a lanthanide with a transition with a transition, and combine and make the materials with the new properties. So, these are some things, some examples we will see in the next class. Thank you very much.